So, a reminder, the first problem set is due on Wednesday at the start of class, so 1 o'clock. It's a deadline, not a target, so don't aim at it. Some people aim at these things. What else? I have my office hours in Alderman Cafe this afternoon, 3 to 5, and then in my office on Wednesday morning, 9 to 11. So if you got questions about the problem set, if you get stuck on stuff, come and talk to me, or after class today. Any questions about the problem set? I mean, other than the answers. All right, look for them on Colab. It's 10 questions, yeah. All right, where things left off. And so today I really need to be sure I get through the material for the last couple of questions on the problem set. And I've sort of done it already, but not carefully. So just remind you where we left off. With ramps, I'm dealing with work and energy. And I'll remind you that energy is what you have. Work is the process of moving it from one thing to another. So you have energy, your friend has energy. You can move energy from yourself to your friend by doing work on your friend. You can also take energy out of your friend by doing negative work on them. And I told you last time that if I don't use the word negative in talking about work, including in a problem, a question on an exam, if I don't say it's negative, we assume it's positive. It's a convention. Do I really care about the convention? Not terribly, but it's so universal that it's worth adhering to. And and I use my joke about it being like giving money to charity. I mean, you'd be pretty much of a heel if you gave negative money to charity. So we don't do it. It's always positive. Work is always positive unless otherwise said so. Is that okay? Or questions about the negative, positive work thing? So to give you an idea, also the issue of the distinction between energy and work, again, it's a naming thing too, but it's a pretty widely used convention. The same thing with money. You spend money. You don't. The act of transferring it is a spending process, or alternatively earning process if it's coming the other way. So you have it, you move it around. We'll see other conserved quantities in nature. There are very few. And they also have an amount that you have, and then an action that you do to transfer them, which has its own name. All right. With energy, you transfer it by doing work. And the recipe for work is very simple and it's a small-scale story. I talk about microscopic. If you want to see whether I am doing work on the ball, pay no attention to anything else in the room. What's apart from my hand and the ball? Nothing else matters. I could be riding a bicycle. I could be on a trampoline, whatever. All that stuff doesn't matter. It's my hand and the ball. And the issue is, am I pushing on it, on the ball? Is my hand pushing on the ball? And is the ball moving a distance in the direction of my push? Nothing else matters. All right? So, right now, I'm pushing on the ball, but the ball is not moving a distance in the direction of my push. So I'm doing no work. On the way up, though, it has to come with sound effects. On the way up, I pushed it upward still, and it moved a distance in the direction of my push. That's work. And it now has energy that I used to have. On the way down, from its I'll do it my perspective. I'm pushing it up still, and it's moving down. That's the wrong direction. It's moving opposite my push. So I'm doing negative work on it. I'm taking energy back out of it. And you can sort of see, when I did work on it, I gave it some energy. It's actually in there. You can look at this thing and examine it and realize it's got more energy than it used to have. It's able to do things it couldn't do before. And when I go back, it lost that energy. It no longer is able to do the things it could have done in the past. All right? Yeah, Dakota? How does it transfer energy to me when I lower it? From its perspective, which I was about sort of tempted to do and didn't do before, it's pushing down on my hand. Everybody okay with that? And my hand is moving a distance in the direction of its push. So it did positive work on me. So that always happens. Whenever you're in a situation where you're doing work on something, on a person, they are simultaneously doing negative work on you. The transaction has both sides, and it always matches perfectly because the forces are always equal and opposite. Yeah. What type of energy? So start naming the types of energy. When I push up on this, it goes from, in this story, it goes from motionless at low altitude to motionless at high altitude. I gave it energy that it now has in the form of gravitational potential energy. And let me stop the story right now so I don't get too sweaty, okay? But we'll come back to that, and I should talk about why you get sweaty too. So I put energy into it, which it now has in gravitational potential energy. Which it now has. What's the form? The name of the form is gravitational potential energy. It's a potential energy, meaning that it's stored in the forces between things or within things. This has a different, I'm going to do work on this spring, this one, because you can see it better. If I stretch this thing, I had to pull each end outward, and it moved outward. I did work on it, right? Can you see that I did work on the spring, stretching it? Both hands did work. The energy now is stored in forces. Within it, it's these springy forces. So that counts too. That's a different potential energy. It's in the spring. The spring can now do things it couldn't do before, like fly around the room. So to go back to gravitational potential energy, because it's useful to start with, when I take the ball from low altitude to high altitude, I clearly did work on it. You're all okay with that idea? The energy now is stored in the force of gravity between this ball and the Earth. I pulled them apart. They would like to be closer together. Again, I could have a smaller ball here today, but I don't. So that energy is really shared. That stored energy is shared by the Earth and the ball. Because the Earth never does much movement, it's so massive, you just can't get much action out of the Earth. We attribute all the gravitational potential energy to the ball itself. We sort of, it's kind of a, is it a trick? I don't know. It's a simplification that the Earth's not going to be doing very much movement. So you can't, when you let the ball and the Earth try to get back together, energy comes back out of the gravitational potential energy. It ends up always going into the ball. If I drop the ball and the Earth will both accelerate towards one another. And will begin to go faster and faster, and will accumulate a different kind of energy, kinetic energy. So by the time the ball hits the floor with big problems, the ball will be traveling fast. The Earth, in principle, will also have accumulated a little bit of upward speed. It will be coming at the ball, but it's so massive you never notice this acceleration. It's a tiny, it's not zero, but it's so small you never notice it. Yeah. Is there an altitude where there's no potential energy? This is, in this case, gravitational potential energy. Not really, because if I say this is zero, this is the zero gravitational potential energy, and it increases, as the last line in this view graph is showing you the extent to which it increases. It increases by the force you exert times the distance you lift. So it's a weight times altitude. The weight of the ball times its altitude tells you how much work was done on it to get it there, and therefore how much energy it has stored. And so weight times altitude, you okay with that idea? So what's the zero? Well, it's similarly, what's the zero of altitude? You take your pick. Sea level is a conventional choice of zero, but if you're willing to drill holes, you can go below it. And so, in principle, you can get to zero gravitational energy in the Earth if you drill a hole into the center and put the ball at the center. It's very artificial, and even that's not a very good zero because there's the sun, and then there's the galaxy. And so we pick zeros and live with it. You can go below zero. Okay? A useful zero for this room would be the floor, because with reasonable effort, you can't go lower than that. But often you get to choose the zero. This might be similar. It's like what does it mean to have zero money? Or, to have absolutely nothing Well, in principle, it's like no bills in your wallet. Well, but you might have something in the bank. So okay, so you get rid of that. You get rid of, it's hard to get to 0, 0, 0. What's 0? You could sell your watch if you have a watch anymore, that kind of stuff. All right? Other questions? Oh, and then the question was, I think your original question was, what happens to the energy on the way back down? Okay, so I missed that part. So don't let me off the hook. On the way back down, the ball goes from having lots of gravitational potential energy to not having it. And I'm sitting here motionless. Where did the energy go? Well, it went into me where I turned it into thermal energy. And so, why am I sweating? It's in part because we're pretty good at taking energy that we obtained in one form and passing it out in another form. The form we like to get energy in is food. And by way of breathing, we breathe in air, we eat food. The two together actually have chemical potential energy that allows us to live. And we can do things like lift the ball up. When the ball comes back down, we can't reconstruct the food energy. Instead, we just grind that energy up into a useless form that generically called thermal energy. It's still energy. It's still the same energy I've talked about up until now. That is, it's composed of energy of motion, so-called kinetic energy, and energy stored in forces, so-called potential energy. It's still those, but it's tiny little pieces sprinkled statistically or randomly, in effect, around among all the atoms and molecules that make up me. And so I get a little hotter. The thermal energy is associated with temperature, and we'll get to that eventually. But if you take, for example, if you rub your hands together, you're doing work a lot of the time because you're pushing on things, they're moving the direction you push. It's a little complicated, and we'll get to that also in the near future. But your hands start feeling hot, your skin feels hot. You're actually turning chemical potential energy, breakfast cereal, or last night's whatever, amusement. You're turning that into thermal energy, right? So what people are good at doing is doing work on other things and then receiving work done on them, chewing it up into nothing. And this explains certain things, like if you go for a hike up and down a hill, a mountain. On the way up, it's actually, in many cases, it's your leg lifting you. You're not a single solid object. You're composed of pieces that do the job. The act of climbing a stair or a hill often involves your leg planting and your knee then lifting the rest of you, doing work on the rest of you. So chemical potential energy that was in your knee and your muscles of your knee lift you up, do work on you, and you're now higher than before. And you do it again, and you do it again. Up you go, and by the time you're at the top of the mountain, you've turned a whole lot of food energy, chemical food energy, into gravitational potential energy. Now you come down. On the way down, you're doing the same thing. Your leg keeps lowering you and doing negative work on you. Plant, lower. It's pushing up on you as you go down. As you go down, it's doing negative work. It's getting rid of the gravitational potential energy. Where does it go? It goes into thermal energy in your leg and your knee. If you're lucky, you hope it's only going into thermal energy. It can also go into tearing things or injuring things. That energy that's coming back out of your gravitational form can injure you, and that's in part why it's challenging to go down steep hills. Yeah? Wouldn't there also be thermal energy when you go up? Yes, there's thermal energy in the going up, certainly, but it's even more apparent when I do this. When I lift this ball up, there are sort of two things happening at once. One is I'm doing real work on the ball. The ball's energy is increasing. That's there. The other thing is I'm getting hot. Why? It's because I'm inefficient. I consume 10 units of food energy to do 5 units of work on the ball. Where'd the other 5 units go? They got ground up in me and became thermal energy. I mean, we're just not 100% efficient. The energy doesn't disappear. Energy is truly conserved. But we don't always transfer all of the energy we consume in food. We chew up some of it, make thermal energy out of it, even when we're at our best. Yeah. Yeah. Yeah, so the question is like human efficiency. As you get more and more in shape, are you putting more of the food energy you're consuming into the work activity and less into the getting hot activity? And the answer is probably yes. I'm not sure. I would say the answer is probably complicated, but probably yes. The most inefficient possible way of lifting the ball, for me, would be go really slowly. Why? Because just holding the ball here, I get tired. I'm doing no work on it at all, and yet I'm chewing up food energy to just hold my muscles still. We make terrible statues. So a statue could do this since the Greeks, okay? The ancient ones, not the current ones. And so there are all kinds of horrible things to add to that. But anyway, so you, there, saved by the bell. So we're terribly inefficient like this. If I go very slowly upward, I'm burning 99% of the food energy just playing statue, and only a little bit is going into the efficiency. So speed likely matters, and the other thing is skill. There's a lot of skill in all of these things. We'll encounter later on one of my favorite examples of things that fascinate me are swimmers. When you get going, when you're moving, you can coast, right? So if you can get started swimming at 10 miles an hour, in principle, and no net force on you, you go 10 miles an hour all day, you could coast from here to Europe, and it would cost nothing. Well, it doesn't happen. Why? It's because you encounter slowing effects of water resistance. So you have to keep propelling yourself forward, and you do this not by pushing yourself, but really getting the water, conspiring to get the water to push you forward. And you do that with your hands and your feet. You throw the water backward, it pushes back and pushes you forward. Well, the water resistance you experience, it's a pretty simple thing to prove, and we'll get there a little bit. It goes as the third power of how fast you're going. That is, if you double your speed, you encounter 8 times as much water resistance. It's terrible, huge increase. And yet, good swimmers are clearly able to swim twice as fast as I can. That means they are producing 8 times the power that I do to propel themselves forward against this horrible rush of water resistance. They're either 8 times as powerful, or there's a lot of efficiency here in how they maneuver. And I think it's a mixture of both. Long answer. Yeah, go ahead. Are robots more efficient? In principle, they should be, because they don't have the wasting effects that we have. Like if they want to lift something, assuming that they've got motors, for example, it can be way into the 90% energy efficient. You put 100 units of energy in a motor, it can put 90 odd units of energy into the actual motion of lifting something, and then it can just hold still all day. So yeah, it can be more efficient than we are. This reminds me that I oh. All right, thank you. All right, Al does most of the demonstration stuff here, so thank you, Al. What was I going to say? Robots and energy efficient. I wanted to name units. I haven't named the units yet. I mean, here I am talking all along about units of energy. The unit of energy is associated with this observation that if I push up on this ball, and let's just for simplicity, let's say I'm exerting 10 newtons, it's more than that, but say 10 newtons, and I lift it 1 meter, the work I do is the force I exert times the distance I move the ball in the direction of the force. 10 newtons times 1 meter, that's 10 newton meters. The units actually work out, they come along in the multiplication. The newton meter is the unit of energy. It's so important. It has its own name. It's called a joule. I did mention joule before, and it's joule, Joule. So in principle, I transfer 10 joules of energy to the ball. When I lower it, it transfers 10 units back to me. All right, so that you will see joules showing up in the problem set. It is the unit of energy. It's one you're actually familiar with, directly or indirectly. If you have, you know of consuming electricity in watts, right? Surely you've used the word watts somewhere along in your life. The watt is a unit not of energy, but of power. Power is energy per unit of time. What's the difference there? It's energy is an amount you have, and work has the same units. You have 10 joules of energy. You can do 10 joules of work on something, and thereby give them 10 units of energy. If you do work steadily, 10 joules every second, for example, so every second you do 10 joules of work on your friend, 10 more joules of work on your friend, 10 more joules. You're doing work at a steady rate. That's energy per unit of time. That's power. That's how much energy you transfer every second, for example. And if you transfer 10 joules every second, the name for a joule per second is the watt. So 10 watts means you're transferring 10 joules every second. And if you've ridden stationary bicycles that tell you how much work you're doing in watts, a couple hundred watts for a human is a lot. I mean, you can feel it when you get above 100 watts of work. So you're doing 100 joules a second, you're starting to sweat. Probably the most people can actually sustain for any length of time is probably between 500 and 1,000. Even trained athletes probably can't sustain above 1,000 joules per second, which is, say, 1,000 watts of power. So questions about this stuff? Okay, so when you buy electricity, you buy it in this bizarre unit known as a kilowatt hour. A kilowatt hour it's 1,000 watts times an hour. That's 3,600 seconds is an hour, and a kilowatt is 1,000 joules per second. If you multiply those together, you get 3.6 million joules. A kilowatt hour is exactly the same as 3.6 million joules of energy. So you're buying when you buy 1 kilowatt hour, which costs about 10 cents, give or take, that's 3.6 million joules. All right. Okay. Other questions about work in, work out, why we're not perfectly efficient? Another thing I better make sure you're clear on is the direction issue. I've done it at times, but I want to make sure I pin it down finally. That when I do work, this is work on the ball, this is negative work on the ball, and this, in principle I'm going steady, is zero work on the ball. Why? Because my forces stop. The force is up, the direction of travel is at right angles to my force. I'm pushing on it, but it's moving not up, not in the direction of my force, not opposite the direction of my force, but across the direction of my force. That doesn't count. And if I go up at an angle like this, my force is up. To know how much work I do on it, it's the distance it travels in the direction of my force, which is up. Only the up part matters. The sideways part of its movement isn't in the direction of my force. It has technically no component in the direction of my force. It doesn't count, okay? So whether I go like this to this, from this height to this height, that uses that was 10 joules I put in. This is still 10 joules. Yeah. Since I'm using more energy during the second part of the activity, where does the rest go? It stays in me. I don't actually transfer to the ball. I do get more tired, but it's all because of my inefficiency. A robot, in principle, could do it without the waste. Sarah? Oh, sorry. Remind me your name? Katie. Got it. Ryan? Okay, sorry. Yeah. Katie. What if I push the ball like that? If the story starts, not yet, now, and it's going at constant velocity, then I'm still doing no work on it, because in this part of the movement, I'm pushing it up as it's moving horizontally. But as I get it started, I have to make it accelerate from motionless to moving away from me towards you guys. That requires me to push it towards you. During that moment, I did work on it. So when you throw a ball, I'm not going to throw a mass, but during the act of throwing it, even though it's horizontal, now I do work on it, because I go from motionless to faster and faster and faster and faster. During that period, I'm pushing it in the direction it's moving, or it's moving in the direction I'm pushing it. That's different. Now I am doing work on it. I am investing energy into it, and the energy is going purely into kinetic. So the act of throwing a ball, even if there's no change in altitude, it involves investing energy into it. So you all go with that? Catching it's the opposite. Catching it involves taking the energy back out of it, which is why you can't catch a ball with brick hands. If you try to catch a ball when it comes at you like that, and you don't give, it can't do work on you. But you want it to do work. You want it to give you the energy. So you catch a ball and you give. And the act of giving allows it to do work on you. You correspondingly do negative work on it and suck the energy out. Yeah. If it's only when it's in your hand that it counts. Because if you're not touching it, you can't exert a force on it. You can't do work or negative work on it. Yeah. Other questions? Again, I appreciate the questions because it's, for 1,000 reasons. And I'll keep trying to get names right. All right. The ramp, to finish the ramp up property here, the value of the ramp doesn't do magic. It allows you to do work while changing the relationship between the force you exert and the distance over which you exert that force. If you're going to lift the wagon, I'll pretend that you're sitting in it, whatever, so I don't get too worn out here. If you want to lift it this high off the ground, you're going to have to do a certain amount of work on it, no matter how you do that lifting. If you go straight up, it's a big force for a small distance. Why? Because you're going to support the entire weight of the wagon. To move it at constant velocity, we won't worry about the starting and stopping process. They'll cancel out. You invest a little extra energy to start, you take a little energy out to stop, they cancel. But the act of going from motionless here to motionless, let's go to a whole meter. To 1 meter, if this is a 10 Newton wagon, you did 10 joules of work. And by going straight up, it's pretty clear. You exerted a 10 Newton force while the wagon moved 1 meter in the direction of your force. You did 10 Newton meters of work. That's 10 joules. It's pure and simple. If you use a ramp, though, watch what happens. Now in the ramp, to go up the ramp, we realize already the ramp starts to help support the weight of the wagon, so you don't have to push with a whole 10 newtons anymore. You push less. And you can make it move at constant velocity up the ramp. Again, we're neglecting the starting and the stopping because they will cancel. To go from motionless to the bottom of the ramp to motionless to the top of the ramp, you had to exert a force that canceled the ramp force while it moved the length of the ramp. Well, to make this ramp capable of lifting the wagon 1 meter, I have to make it longer. So here it is, we're out here, okay? We now got it to 1 meter. To get it to go up that ramp from the bottom to the top, I had to exert a small force. Let's say about, just for simplicity, about 2 newtons. Not the full weight of the wagon, only 1/5 of the weight of the wagon. You're okay with that? But I had to make it move 5 times as far, 5 meters along that ramp. So I used a much smaller force by a factor of 5, but I had to move the wagon 5 times as far in the distance of my force. I push it uphill, and it moved uphill. I did work on it, direction in both directions. So I did 10 joules of work again, 10 Newton meters of work. I just did it with a small force over a long distance. And playing with the ramp, if you make the ramp perfectly steep, you get 1 meter of altitude for 1 meter of travel along the ramp. You have to support the entire weight of the wagon, so a big force, but little distance traveled. The product of the two, force times the distance the wagon travels, 10 newtons, 10 Newton meters. Same as synonymous with 10 joules. If you make a ramp that's fairly steep, you use only 2 newtons of force, but you have to move 5 meters now to get up to the height you had in mind. And if you make the ramp even shallower, just a wimpy little ramp here, this might be, you only need half a newton of force, but you might need 20 meters of ramp to get to the altitude you're going for. The product's always the same. So where does this take us? It's the act of investing a certain amount of energy in the wagon to go from the wagon at altitudes, let's say this is altitude 0. We get to choose it. So we just say that's the altitude which we call 0, that's sea level, and this is 1 meter above it. And when it's 1 meter up, it has some gravitational potential energy that it did not have down here at sea level. How much energy? 10 newton meters or 10 joules. If you want to take the wagon from sea level to 1 meter, you're going to have to invest 10 newton meters or 10 joules of energy in it, however you like. You can put it in your back pocket, you can walk around for a week, and you can come back and plop it on the shelf up here at 1 meter, and you will have transferred, on the grand scheme of things, 10 newton meters to it, nothing else. Everything else is fun and games. You can throw it up to 1 meter. It won't be there very long, but when it's there, you will have, that will have transferred into it 10 newton meters of work. Same as always. So the path doesn't matter. Go up a steep hill, go up a shallow hill. If you go from the bottom of the hill to the top of the hill, the energy transfer is the same. And that ultimately is why, a reason why energy is so useful as a concept. It's because you can figure out what's going on in a situation by following the energy. It's like follow the money. If you want to see how some crazy, complicated company is whatever is going to work, one approach is to follow the money. If you want to see how a mechanical system is working, follow the energy. You'll see it move from piece to piece to piece, never disappearing, never being created. It may go from one form to another. It may go from kinetic to potential to kinetic. I mean, when I do this, it's going from me in chemical potential form to kinetic form in the wagon when it reaches peak speed down here low, to gravitational, back to kinetic, and back into me where it becomes thermal. So it's moving all over the place. But you can follow the whole flow and ideally learn a fair amount about the system and the situation. All right? Questions about, so just to finish the naming of things, I think I have a statement here. Mechanical advantage. In all likelihood, somewhere in K through 12, you talked about the simple machines and what the simple machines do, technically what they do, what a ramp does. But sort of what was missing in all likelihood was the big picture. What the heck is the point of a ramp? Yeah, it's an inclined plane. You now have this fancy 2-word noun. You can sound sophisticated. What the heck is it doing? Most of the simple machines perform a simple function of providing what's called mechanical advantage. They allow you to do the work that you have in mind to do, with a different relationship between force and distance. So you're going to do the same work you did. For example, lifting, you want to lift your entire car off the ground to change a tire instead of calling the service, right? You want to do it yourself. Well, if you go and try to lift the car, most of you probably cannot do this unless it's a Matchbox car. You're going to need something to work with. You use levers, and most jacks are sophisticated levers. They allow you, if you think of hopefully you know what a lever is. You've dealt with levers somewhere along the line. This is a lever, right? If I want to lift something really heavy, okay? Jumbo the elephant sitting on that end. I want to lift Jumbo up, okay? I can push down on my end of the lever, and we'll talk a bit about the next topic is seesaws, which are basically levers. If I push down on my side of the lever, it moves a long distance, right? See my hand go up and down? A foot. Whereas Jumbo's foot over there only moves up and down a couple inches. I do work in pushing this lever down as it moves down. That lever does work in pushing Jumbo up as Jumbo moves up. But I have more distance to work with, so the force I use is small. Whereas that lever travels a short distance with a big force. And the bottom line is I can push down gently on my side of the lever and cause it to push up ferociously on its side of the lever and lift a very heavy object. The work done, however, is the same. I push down with a gentle force for a long distance to do the work, whereas it pushes up on Jumbo with a huge force, but only over a little distance. It does my work on Jumbo with a different balance between force and distance. I'm waving my hands a bit because I can. Hopefully you can follow that idea. So most of the simple machines, the levers, the inclined planes, gosh, pulleys are a little more complicated, although complicated pulleys do this again. They allow you to do the same work you wanted to do with different force-distance relationships. All right? And certainly that's true of ramp. That's my story for ramps. So let me move on to the next topic, which is seesaws. And seesaws, I've suffered over this particular topic. They're my excuse for bringing in the world of rotation, because seesaws actually rotate. They rotate about a pivot. They're not allowed to rotate all the way because you hit the ground eventually. The problem with seesaws is, they're pretty much gone. I hope that some of you have ridden a seesaw, but they were everywhere when I was a kid. They're essentially non-existent. And I don't know whether it's the lawyers that got them or whether it's people are just too bored. I'm tempted to write an app, seesaw app, so at least people are like, oh, I got a seesaw. Yeah, but I could go on forever talking about the change in the world. But hopefully at least you have some familiarity with seesaws, at least in concept. I'll show you why I think, in part, it's the lawyers that got them. It's because two kids playing merrily away on a seesaw, it's a balanced lever, and the concept of balance is itself an interesting one that we'll come to. So this is a seesaw with two kids riding back and forth. They tip it back and forth, and it's undergoing very simple motion that is rotational in character, which is the point of bringing it up. But a major problem with seesaws is that kid sees something interesting over here and just decides to leave. And the other kid now has a 911 experience. All right? The other version of this is this kid's out here, and along comes big guy, right? Oh yeah, I'll play with you. Woo! Okay? And this was the early space program. All right. So, all right, a seemingly unrelated question that I'll probably have to answer because it'll eat into the end of the hour. I'm getting sticks for a reason. The question is this: there's you, big tall you, and short kid. And the two of you simultaneously stand on the edge of the pool. There's the pool. Here's the edge. And the two of you lean out over the pool, holding on to something. You lean to the same angle, and then you simultaneously let go, and you tip over into the pool. You picture that? The question is, who hits the water first? You okay, the question? How many think that you hit the water first? Big, tall you hit the water first. How many think the kid hits the water first? Okay. There's a majority, not plurality going for the kid. A lot of non-voters here. So make your decision secretly so no one will know. And I'm going to let them both go at the same time. And you can watch who hits the water first. It's not even close. The little kid hits first. Did you see that? I'll let you watch it again so you can see. So the short thing goes over much faster than the tall thing. And to give you an inkling of why is that, it's because this is a rotary story, this is a rotational story as well. You're both rotating about your feet. That's a rotation. And just as with everything I've talked to you up until this point, there are physical quantities that describe rotational motion that are very like the physical quantities we've talked about till now, but they're modified to be rotationally connected. For example, there is a rotational equivalent of position, which is which angle something is at. A little more complicated than that, but that's the basic idea. And there is a rotational equivalent of velocity, which is how fast something's rotating. And there's even a rotational equivalent of acceleration, which is how fast this rotational velocity is changing with time. There are two more quantities to pay attention to. One of them is the influence that causes rotational acceleration. And that's it's not called a force anymore. Forces are for making things accelerate. To make things rotate or stop rotating or rotate differently, you twist them. And the sophisticated name for a twist, the physics name for a twist is a torque. T-O-R-Q-U-E, torque. So I can exert a torque on this stick, ready, gets that torque, okay? And that causes it to undergo a change in its rotational velocity, which is, in fact, a rotational acceleration. The last piece of physical quantity to pay attention to is an object's rotational inertia, its tendency to keep doing what it was doing. And this has a relatively little rotational inertia. I can make it go from rotating that way to rotating this way with little effort, modest torque. This, on the other hand, and this is one of these cases where come down secretly after class when no one's watching and try twisting this guy back and forth. This thing's 8 times as hard. By virtue of it's twice as long, it's way harder to make it undergo the angular change, the change in angular velocity. Much harder, and that's the dominant effect in the two kids falling over. The two kids falling over, the most important issue is their ability to respond to torques. And the little guy responds easily, the big guy, much harder. And where does that show up in the real world? It shows up in things tipping over, like trees, tall. They used to take down industrial chimneys. I'm not sure how many giant industrial chimneys are still around anymore, but they used to be in the era of powering everything with coal, for example. They would have just an enormous chimney that would go way up to try to get the sooty stuff out of normal, to let it go to the next county and mess up their air. So you have these giant chimneys, and to bring them down, it's like, oh my God, what do we do? So they would somehow cause the thing to tip over. But it's the same with a very tall tree. Timber, the thing falls over. It doesn't go like thunk. It's slow, really slow, because it's like you on steroids. Hopefully not. Okay, I'll stop. Curb my enthusiasm. Trying to fall out. It's very slow to fall over. And public service announcement, part of this is they tend to break as they go over because they have internal stresses. This battle of trying to fall over, they want to become short. The first part would love to become a short thing that can fall over quickly. So it will typically break free of the other part. So it will break, and the bottom of a tree, for example, an old dead tree that's really in bad shape and doesn't have much strength left, when you cut it to have it fall over, it will start to fall, and then it will break right about here, and the bottom part will tip over fast because now it's happy, it's short. And the top part now is not rotating at all, it just drops. It's not connected to the ground anymore. It's not a tipping thing, it's just a dropping thing. And people get smushed by that thing coming down. And it is a common tree cutter's mishap. This is why you get the professionals in there to cut your trees down. If you do it as an amateur, be aware that if your tree is a rotten old thing, you may have this thing drop on you. It may break during the fall. Can you follow that idea? Or questions about that idea? And we have a family friend, former professor at the university, who was paralyzed by the tree falling on him. I mean, he spent the past 30 years in a wheelchair for that problem. All right? All right, with that public service announcement, I'm going to call it a day. It's Labor Day. Have a,